Another family of properties of definite integrals is that integrals tend to be, well, are linear functions or linear operations. What that means for us is that if we know the integral of something simple, for example, the integral from a to b of some function equals 10, then we can predict what will happen if we multiply that function inside by 5. And it's not hard to do. Let's do the obvious thing, which is if we multiply by 5, then we expect things to get 5 times as big. So let's take that right off. The integral from a to b of 5f of x is going to be as if we could bring the 5 out front, and that's going to equal 5 times this part we know is equal to 10, so we can replace that here and we'll get 50. The question is, why is that the case? Well, if we imagine any function that we might have, let's draw it down here at the bottom. If we have some function that's doing its thing, and between the point A and the point B, the x-coordinates there, we have an area of 10. Ignore the integral for a second and just ask what happens when we multiply that function by 5. Well, if we put a multiplier out front of a function, that scales it by 5. 1, 2, 3, 4, 5, I think is there. So the function that's 5f of x is going to look like this. That's y equals 5f of x. The interval is exactly the same. The interval of integration is a to b again. And now we're talking about this region here. Well, if we scale the vertical axis by 5, we expect the resulting area to be scaled by 5 as well. The x interval is the same, but we've magnified everything in the other direction. That's going to produce a growth by a factor of 5. What about combining functions like this? Same kind of argument can be made, and it's exactly what you'd expect, so this is nice. If we have the integral of f on an interval is 2, and the integral on a to b of g is 4, then what do we expect? We expect that we can compute these two things separately. The integral from a to b of f plus the integral from a to b of g, we can compute this as two separate objects and get simply 2 plus 4, which will be 6. What's the area analogy for this? It's a little harder to see sometimes. Let's keep it simple. Let's keep it as blocks for now. Let's say that's our function f of x, which has an area of 2, and then g of x would be twice as high. They don't have to be constant, but it'll make the picture a lot easier to draw. So this whole area here is 4. If we, again, ignore the integral for a second and simply look at the function f of x plus g of x, what do we do to get that? We add the heights. So we would add the heights of f and g, and we'd get up to here. This would be the graph of y equals f of x plus g of x. It will be all the way up here, and of course it's like taking the f function and putting it on top of the g function, so the areas also accumulate, and the area there would be 6. Let's get these annotated. And again, it just comes from the stacking vertically of these various pieces. Areas stack vertically, so the areas are added. And that gives us a rationale for why we can add functions together inside an integral and actually treat them as if they're being added separately as separate integrals. Here's a quick summary of those results. If we put any constant inside an integral, we can bring the constant out front. And whenever we had the integral of one function plus another or one function minus another, we can divide it into separate pieces as well and integrate each of these sums separately. Notice, this does not say anything about multiplication by functions, so excluded. multiplication between functions. Multiplication between two functions. We cannot have the integral of x times x squared dx equals integral of x times integral of x squared. We see it on exams all the time, but it is not true. If it was true, we would spend a lot less time studying integration because it would be a whole lot easier. So just remember, we've got constant multipliers, and it's constant is the key word there. Constant multipliers, and we have addition and subtraction. Those relationships or those transformations of a function transform the integral in very predictable ways. Products of functions, not so much.